This video is going to go over regression models. And so first thing we're going to do is we're going to fit functions to data. So in statistics, when you have data, you try to find which function would be the best fit for that data. Now, it's not going to be exact because data varies, but we try to find which one we think is the best model for what's being represented. And the three that we're going to focus on today are a linear model. Remember, that's a straight line. A quadratic model, that is a parabola, or an exponential function, which, if you remember, we had growth and decay, kind of follows those, that type of a shape right there. So for the first one, we have a scatter plot here, and I want to see what type of shape I think would best fit all of these dots. And I think I could pretty carefully draw a fairly straight line through this scatter plot of data. And so for this one, I would say that a linear model is best because it looks like it follows that constant straight line. Now looking at a table, for the table, you really want to focus on the y values and how the y values change as the x's are increasing. So I'm going to look and see how y is changing from one point to the next. So from 1 to 9, we are increasing, and we increased by, well, technically we added 8, so maybe there's something there that you are adding 8. We'll see. We'll try again. 9 to 18, we are increasing by 9. Okay, so right away I can see it's not quite constant, but that's okay. All right, from 18 to 21, I would increase by 3. I got a little bit lower here. And now on the next side, 21 to 19, ooh, now we're decreasing by 2. Okay, from 19 to 8, we are decreasing by 11. And from 8 to 1, we decrease by 7. So based on what I have here, it's not really a very constant rate of increase or decrease. But what I do notice is that this graph has both increasing sections where it's increasing by a set number, and then it also has decreasing sections. Out of these three options, linear, quadratic, and exponential, only one of them has both an increasing and a decreasing section, and it's the one that looks like this. All right, we start out by increasing, and then it switches and starts to decrease. That is the parabola. So for the table, the best model would be quadratic. And the last one, again, I'm going to try to fit the best model to this. If you try to do a straight line, while it looks like you've got the front dots here and the back dots, it dips below the line in this section. So a linear function is not going to be the best one here. What's actually going to be better is an exponential. So remember that shape, it kind of starts slowly and then it quickly increases. That is the shape of an exponential, and that seems to fit pretty well. So we're going to start to look at this a little bit deeper today. We're going to analyze data sets to choose the appropriate regression models through the use of technology using Desmos. So if you don't have Desmos out, go ahead and get it out or get a tab open with it. We're going to look at the pelican population. A team of wildlife conservationists and marine biologists has been studying the population of pelicans in a region since 2010. The table shows the estimated number of pelicans in different years. What do you notice and wonder about the data? Describe the distribution. So we start at year 0, then we go to year 1, 2, 3, we skip 4, 5, 6, skip 7, 8, skip 9, 10. So this is just the year since 2010. This would technically be our X value, it's time. And then the Y value, the number of pelicans in thousands. It starts at 5.2 thousand, and then it's decreasing to 4.5, then it decreases to 4.1, then it decreases to 3.9, but now it increases to 4.1, and then it increases to 4.4, increases to 5.7, and increases to 7.5. So what do I notice and wonder about the data? Maybe I'm wondering, why does it skip some years in here? But even though it does skip a few years, we can still look at the pattern of the y values. But one thing that I'm noticing is that the y values have both intervals of decrease and of increase as we go from left to right on the x-axis. And so for this one, I would describe it as probably being a quadratic due to the fact that it has both increase and decrease. Now let's actually plot this and see if we get a better idea of the shape. So I'm going to start, we've got 0, 5.2, 1, 4.5, 2, 4.1, 3, 3.9, 5, 4.1, 6, 4.4, 8, 5.7, and 10, 7.5. All right, so we don't have a perfect picture because, again, we were missing a few years, and I also plotted 1 point wrong here at 2.5. So let's fix this one. 3 is at 3.9. There we go. So we are missing a few, but you can see this swoop shape that looks like a very lovely parabola. There we go. So yeah, I would agree, still looking like a parabola shape because it has both the increase and decrease sections. Now we're going to actually use technology to find the best model. So we will first plot these points on a scatter plot, and then we'll test to see the regression model that fits best, or see if our regression model fits best. In Desmos, so the first thing we want to do is add our points to the scatter plot, and we're going to do that by adding a table. So up at the top, you see there's a plus sign, the top left above that one that's in blue. I'm going to click plus, hit the table option, and I'm going to start to type in my x values. So we have 0, 1, 2, 3, 5, 6, 8, 10. And then for the y values, 5.2, 4.5, 4.1, 3.9, 4.1, 4.4, 5.7, and 7.5. All right, and so now we can see the same image that we had drawn on our scatter plot together, but now we want to see if we can find the potential line of best fit. So what I'm going to do is I'm going to type in y1, and then we're going to use the little squiggly line. I'm going to see if I can find it in here. It's right down here, that squiggly line. It's called a tilde, actually. And now what we're going to do is type in the function that we think is the best fit for the scatter plot. So we had said we thought a quadratic model would be best because this scatter plot has both decrease and increase intervals. So I'm going to go ahead and type in the standard form for a quadratic. So we have x squared, oops, I need to actually do x1, x1 squared, okay, plus bx one plus c. So we type in standard form for a quadratic, and we use y1 and x1 because that's what our table is. Our CR table has x1 and y1 at the top. So now when we plot this, notice that we now have a quadratic that seems to fit our points very well. It's not perfect, you know, this one's a little bit above, this one's a little bit below, but that's why it's called the model of best fit. It tries to get in between all of the points. And so down here under the parameters, it gives us the equation that would be the best fit quadratic model. So we just put A, B, and C into standard form, and now we have the quadratic model that's the best fit for this set of data. So down here we have a picture of what we just found on Desmos, and I'm going to write our equation that we found here. So we have the equation y equals A was 0.09. I'm going to estimate it to be 2 decimal places. X squared minus 0.66x plus 5.12. Again, just to remind you, those numbers came from right here in the parameters. That's 0.09 for A, negative 0.66 for B, and then the 5.12 when we round it to 2 decimal places for C. So that's where I got those values from to get the equation for our quadratic of best fit. Now, question 4 says, state the domain and range of your function. How do they compare to the domain and range of this problem situation? Well, for a general quadratic function, the domain is all real numbers. So that means from negative infinity to infinity. The range for this, now it's going to actually be helpful to go back to Desmos to see the exact range. Because in Desmos, we can click on this quadratic and find its vertex. And the vertex is at 3.659, 3.903. Now, if you had to find this by hand, remember we've learned a few different ways to find the vertex of a quadratic model. For this specific equation, you would use the negative b over 2a to find x, plug that in to find y. But right here, I can see that it's 3.903 on the graph. So the range goes from 3.903 to infinity. Now, how do they compare to the domain and range of this problem? The domain and range of this problem, domain is here. The domain would be from 0 to 10. The range here, well, if I look at the range in y values, we're going to go from low to high. So the lowest value we have is 3.9. And then the highest value that we have within this data set is 7.5. So how does this relate to the domain and range that we have from the model? Well, for domain 0 to 10, this is included in the domain of the quadratic model. The domain from our word problem, remember a lot of times it changes for word problems because time doesn't go on forever and ever in just this situation, right? They're not going to watch the pelicans forever and ever. They watch them for 10 years. And then for range, though, one thing that I do notice is just a slight thing here is that the range for our data starts at 3.9, but the range for our quadratic model starts at 3.903. So actually, our data it goes lower than the range of our quadratic model. That's okay though, because we're just trying to find the model of best fit, but it's good to notice the difference between those. Question 5, use the regression equation to answer each question. I'm going to copy this equation that we already wrote up here and bring it down with us. So now we have our regression model, and we can use it to answer these questions. Part A, determine the y-intercept and interpret its meaning in the terms of this scenario. Well, the y-intercept in standard form is always just c, because when you plug in 0 for x, every term that has an x would become 0. So we get 5.12 as the y-intercept when x is 0. So 0, 5.12. Now, what does this mean in terms of the scenario? Remember for this scenario that x is the number of years since 2010. Is that? Yep, since 2010. And then y is going to be the population of pelicans in thousands. So when I relate this to the scenario, if x is 0, that means that no years have passed. So that means we're starting in 2010. The population of pelicans starts at approximately 5.12 thousand. Or you could actually write it out as 5,120. Part B, determine the x-intercepts and interpret the meaning in terms of each in terms of this problem situation. All right, so we're going to find the x-intercepts for this, and I can tell because of the decimals, it's probably not going to factor. So what that means is we are going to use quadratic formula. We have our a, b, and c, and we will plug those in. So if x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so I'm going to plug this into my calculator, and I get 0.66 plus or minus the square root of in the parenthesis, or under the radical, I get negative 1.4076 divided by 0.18. All right, and here, now that we've gotten to this step, what I notice is that we have a negative under the radical. So that means that this has no real solutions, and they're actually imaginary. So what does that mean in terms of this problem situation? If there's no x-intercepts, remember x-intercepts are when y is 0. That's saying that the pelican number would be at 0. So there is no time when the pelicans will go extinct. That's what this means in terms of this model. Which is great news for the pelicans. Now, what about on the graph that we looked at here? Let's see if we see that as well. Yep, so if you look at our quadratic model we had, look, it never touches the x-axis. It starts above and it increases, or it's pointing up on both sides. So it will never cross the x-axis. Part C says, predict the number of pelicans in the region in 2014 and 2019. All right, so if I'm going to predict for 2014 and 2019, first thing I need to do is figure out what I'm going to plug in. Let's start with 2014, okay? For 2014, if x is the number of years since 2010, then that's saying predict the number of pelicans for x equals 4, because 2014 is 4 years after 2010. So what we're going to do is take our equation, and I'm going to plug in 4 for x. I'm going to use my calculator to simplify this. And when I plug it all in, I get y equals 3.92. So in the year 2014, there will be approximately 3,920 pelicans. Let's try 2019 now. So for 2019, that would be 9 years after 2010. So that would be x equals 9. I'm going to plug in. We've got y equals 0.09 times 9 squared minus 0.66 times 9 plus 500 or 5.12. Sorry. All right, so I'm going to plug this in. 0.09 times 9 squared minus 0.66 times 9 plus 5.12. And I get y equals 6.47. So in 2019, there will be approximately 6,470 pelicans. Again, this is a prediction. And the way that regression models work is that we use them to predict what the y value will be in X number of years or minutes or whatever the model is talking about.